Welcome to Hypersonic Airplanes. This video is brought to you by María Aguirre Romero, Jesús Blanco Fiscal, Renata Roldán del Monte, Erika Márquez Rosas, Damián Torres Ferrón, and Natalia López Guzmán.
So, why don't we have real hypersonic airplanes yet? That's what we are here to talk about today. What's holding us back from creating these super fast next-gen aircraft, and what the challenges are in making them a reality.
When we talk about hypersonic speed, we are referring to velocities equal to or greater than Mach 5, meaning 5 times the speed of sound, approximately 6,174 km per hour at sea level. Hypersonic flight occurs in the upper atmosphere, where aerodynamic heating and shock waves significantly impact vehicle design and performance. This speed range is crucial for military applications, space exploration, and high-speed transportation. Hypersonic technology involves scramjet engines, advanced heat-resistant materials, and innovative aerodynamic designs. Countries like the United States, China, and Russia are investing in hypersonic weapons and aircraft due to their strategic advantages.
Building a hypersonic airplane is no small task. There are a lot of challenges. First, weather and atmospheric conditions. The altitude, temperature, pressure, and weather all play a huge role in how these airplanes behave. Next, we have materials. We need materials that can handle crazy high speeds and the intense heat that comes with it. Later, engine and design. Traditional engines don't cut at these speeds. We need new kinds of engines that can work at hypersonic velocities. And finally, aircraft structure. The plane's internal structure, or chassis, needs to be strong and lightweighted. But at such high speeds, the design has to be super precise. Too big or too small, and it just won't work.
At these speeds, the way air interacts with the plane changes completely. You get massive shock waves, and the friction with the air generates extreme heat. To deal with all of that, a hypersonic aircraft needs special shapes, like slicks, pointed fuselages, and integrated wings, which help reduce drag and control the airflow.
Hypersonic aircraft cannot use conventional engines due to low efficiency at these speeds. Instead, they use scramjets or supersonic combustion ramjets, which are jet engines with no moving parts that compress air to supersonic speeds before combustion. For example, the NASA X-43. Rockets. Some vehicles, such as the X-15, use rocket engines to reach extreme speeds. And hybrid turbines, combinations of conventional engines and scramjets to achieve more efficient takeoffs.
When you're flying at hypersonic speeds, the temperature of the airframe can hit over 2,000 degrees Celsius, which is insanely hot. To keep the airframe from melting, we use materials like ceramics, titanium alloys, and carbon composites, along with cooling systems that help dissipate the heat.
Traditional control surfaces, like flaps or ailerons, don't work well at these speeds. So, engineers rely on advanced techniques like moving surfaces, fluid injection, and thrust vectoring, which helps steer the aircraft without relying on old-school methods. For spacecrafts, precise maneuvers are also crucial for re-entry. You want to avoid burning up from the friction.
The main applications of hypersonic airplanes are military. Hypersonic missiles, such as the Russian Avangard or the American ARRW, and spy planes, such as the SR-72 concept. Scientific and space, development of reusable spacecraft for quick access to space. And commercial, hopefully for the future, transcontinental flights in minutes instead of hours. Hypersonic aircraft remains an active field of research due to technical challenges, but their revolutionary potential is enormous.
We just stated that hypersonic speed is faster than Mach 5, over 5 times the speed of sound, around 6,174 km per hour. Going faster than sound means breaking through the sound barrier, which starts at what science call Mach 1. This is called overlapping. Yet, the sound barrier breaks between Mach 1.2 and 5. This is called supersonic speed. Once Mach 5 is crossed, the speed is considered hypersonic. At this point, overlapping starts tearing apart, when the shock cone creates the point of more tension in the sound barrier. Here is where the sonic boom occurs, and the sonic barrier gets broken, as we can appreciate in the demonstration. To safely cause the sonic boom and break the sonic barrier, the aircraft needs an isosceles triangle design where the pointed front should contemplate space for the engines. For military use, it should also consider room for weapons. There is already a historical precedent of a supersonic commercial plane called the Aerospatiale BAC Concorde. This aircraft was considered the peak of engineering as a cooperation between French and British enterprises. 20 airplanes were built and run between 1976 and 2003. The Concorde fell in disuse after a terrible accident that caused the death of more than 100 people. This was primarily caused by a tire blowout on the takeoff due to a piece of metal on the runway, leading to a fuel tank rupture and a subsequent fire.
Ladies and gentlemen, welcome to Jean Piaget's auditorium. The local time is uncertain. Please remain seated with your seatbelts fastened and ensure the tray tables are stowed. The captain will turn up the fasten seatbelt sign when it is safe to do so. Thank you for flying with us today, and we hope you enjoy your stay at Jean Piaget's.